Ben, thank you very much for the kind introduction. Good morning, everybody. So first, the bad news, no, I don't have any free samples, I'm sorry. But I have something much better. I have a piece of rock, which I'd like to pass around. The health and safety warning is quite heavy, so don't drop it on your foot, so pass it around while I'm speaking. And this is a piece of Kimberley, which is the host rock of diamond. It comes from one of the most famous diamond mines in the world, formerly called the Premier Mine in South Africa, now the Cullinan Mine. The source of many of the famous diamonds of recent history. You can see why the old timers called it blue ground. It's a sort of bluey-grey colour. And kimberlite is very heterogeneous. It means it has lots and lots of different minerals in it. In fact, I think I'm right in saying that most of the common minerals in the geologist's mineral list have been found in kimberlite at some time or another. So kimberlite is actually really interesting in its own right. Some of them, not many, contain diamond. Most kimberlites don't contain diamond, but some do, and they're the main source of natural diamond today. And yes, there's a finite chance there's a diamond in here, so I would like it back in one piece. All right, here's a little quiz question for you. Well, before we go there, let's just agree on the unit of weight for diamond, because I'm going to use this quite a bit. The carat is 0.2 of a gram, so it's 5 carats per gram, 200 milligrams, and it comes from the carob tree, which is native to the Mediterranean and the Middle East area, and the seeds from the carob tree have actually been used to weigh gemstones for a long time. So you'd weigh them and quote them as so many carob seeds. And when it was decided to regularize this, they weighed the seeds on a proper balance and found that they were around about 0.2 grams. So in 1907, the metric carat was defined as 200 milligrams. All right, here's a question for you. What's the largest diamond ever found?
Allegedly the Cullinan. Isn't there one in Brazil even bigger?
I wish Monroe wouldn't come to me. Actually, the last time I gave a talk on diamond was about 30 years ago, and one of them was, in fact, up at Mount Isa with the Monroe, so you probably remember. Yes, it was a diamond called the Sergio, found in Brazil in 1893. It's a piece of carbonado. Carbonado is very interesting stuff. It is diamond, it's polycrystalline, with a little bit of unreacted graphite and other bits and pieces in it. It's only found in 2 countries in the world, Central African Republic and Brazil. There is no known host rock of carbonado. And in fact, the most plausible theory for the origin of carbonado is that it's extraterrestrial. It came from an early planetary body that broke up early in the life of the solar system and spread itself around the place, including Earth. They're quite rare, and you can see they're not exactly gems, so they're largely used for industrial exploration. So that's 3,167 carats, or about 630 grams. But Peter's quite right, and as many of you know, the largest gem diamond ever found was the Cullinan Diamond, which was found at the aforesaid Premier Mine in 1905, 3,106 carats, slightly smaller than the Sergio. You can see how big it is from the chap holding it. I've got quite small hands, and the Cullinan was bigger than my fist, so the gentleman out there with bigger hands, if you make a fist, that's about the size of the Cullinan diamond. And it was found 3 years after the mine started in 1902, allegedly about there. It was found by a worker who noticed it sticking out of the sidewall, shining in the sun, and the surface manager, Frederick Wells, was called over and he prized it out with his penknife, and he couldn't believe what he got, took it down to the mine office. The majority of people said that's not a diamond, it's a piece of glass, and the mythology has it that one of them chucked it out the window and said, let's get on with our work. Fortunately, somebody went around and picked it up, and the rest, as they say, is history. This is a famous picture, because here is the general manager, Thomas McCarty, handing the diamond to the owner of the mine, Thomas Major Cullinan, after whom the diamond is named. It was then bought by the government of the Boer Republic of the Transvaal. This was 3 years after the end of the Boer War, and it was bought by that republic and given to the reigning monarch Edward VII as an act of reconciliation. I bet you they wish they hadn't done that and that they'd still got the diamond. But it was a remarkable act. And so it ended up in the British Crown Jewels, basically. That's an old picture of Premier some years ago, but it gives you an idea of the size of the operation. The Cullinan was allegedly found around about there. It was cut into over 100 stones. The top 9 are the famous ones, and here they are after cutting. This is Cullinan 1 at 530 carats, Cullinan 2 at 317 carats. Those are the 2 largest faceted white gem diamonds in the world, and they are both in the British Crown Jewels now. This is Cullinan 1. This is very rarely used. It's only used at coronation, so it hasn't been used for a while. This is in the Imperial State Crown, which is used regularly at the State Opening of Parliament in Britain. And it sits below, interestingly, this huge red gem, which is the Black Prince's ruby. In fact, it's not a ruby, it's the world's largest uncut spinel, but it was given to the Black Prince. The Black Prince, if you've forgotten your British history, was Edward III's son, and it was given to him in 1367, and it was allegedly worn in a helmet by Henry V at the Battle of Agincourt in 1415. So there's a lot of history in this stuff. But there's Cullinan 1, there's Cullinan 2. Here are Cullinans 3 and 4, which is made into this pendant, which I understand the present Queen does wear quite often. These are called by the family Granny's chips, on the grounds that they were the chips that were left over after the big ones were first cut. And there's a picture in the archives. It's a most extraordinary photograph. It's Queen Mary, who is the daughter-in-law of Edward VII, who received the diamond and had it cut. And she's wearing some pretty impressive stuff. You might think these two are these two. They're not. They're Cullinans 1 and 2 before they went into the Crown Jewels. This is Cullinan 4, and there's Cullinan 3, just below the famous Koh-i-Noor diamond. So she's wearing 5 of the most famous and largest cut diamonds in the world. And I think that was a one-off. I don't think it happened before. Anyway, enough of the Cullinan. The second largest diamond ever found was found 3 years ago at the Karowe Mine in Botswana, very well known for its large diamonds. And there it is. Lesedi Larona, I think, means our light in the local language, Botswana. And it was 1109 carats. So the second biggest diamond in the world was only barely a third of the size of the Cullinan. So the Cullinan really is something a bit special. It was sold very recently for $53 million US. Now, this one I have a personal connection to, as I can't resist showing you this photograph. This is the second largest diamond ever found at the Premier Mine, after the Cullinan. And it was found while I was working for De Beers at the Technical Centre in Johannesburg, and all big diamonds and interesting diamonds came to us to be examined, so I've actually handled this stuff. Now, it started life as an 831 carat stone, but it had a rather difficult beginning because it was found underground by a worker who wasn't sure whether it was a diamond. He thought it was a bit of something else, resin. And he knew diamonds were hard, so he whacked it with a hammer. And he reduced it from 831 to initially 2 pieces. So a 75 carat chip broke off. That's this bit here. This gentleman, who was a colleague of mine, is holding it together for the purposes of the photograph. And later on, when we were handling it, another 1 carat bit drops off. That's this bit. But it left a 755 carat stone, which is not bad. The problem with this stone is that it's not really a true gem. It's brown, it's yellow, it's got lots of inclusions, lots of flaws, and it's classed as near gem. But De Beers decided to use it to test some new cutting techniques, and they got a very famous cutter in Antwerp called Gabriel, who's still around, to cut this, and they were just trying some new things. But he was a bit naughty. He decided he was going to make it the biggest faceted diamond in the world, which he succeeded in doing. It's 15 carat bigger than Cullinan 1. But it doesn't really count because Cullinan 1, the real gem, really isn't. It ended up in the Crown Jewels of Thailand. It was given to the King of Thailand as a 50th Jubilee present. Why it's called Jubilee diamond. So let's say something a bit about diamond. Its structure is a tetrahedral arrangement of carbon atoms, so each carbon atom is attached to 4 other carbon atoms by covalent bonds. And if you put all that together, you get a structure that looks like this, and this is the structure responsible for the remarkable properties of diamond, which I'll come to in a minute. But it's really the archetype covalent material. It's a single molecule that makes the crystal of diamond. You can see it a little bit better here. If you follow one of these diamonds, one of these carbon atoms, you'll see it's connected always to 4 others. It's an allotrope of carbon. There's quite a lot of allotropes these days. The best known one, of course, being graphite. The classic habit in which natural diamond is found is an octahedral shape like this. And you do find diamonds like that, but they grow in every possible way. So diamonds come in all shapes, all sizes, all colours. And a lot of diamonds just don't look like diamonds at all. You need a tutored eye to realise they are diamonds. Colours in particular are quite interesting. Our domestic diamond mine here in Australia is, as you know, I'm sure, Argyle in the Kimberleys in Western Australia. Its diamonds are not very good quality. They're dominantly industrial. But the Gen ones have some very nice features. This is what I would call a yellow-brown diamond. Argyle, of course, calls champagne, which is a masterpiece of public relations. You'd much rather buy a champagne diamond than a brown one. But they are genuinely known for their pinks. The pinks are very rare indeed. Colour comes from inclusions of elements in the diamond lattice. Yellow is generally nitrogen, blue is generally boron, and also some crystal lattice imperfections also give colour. So these pinks are something very special, and of course Argyle makes a lot of that. Where do they come from? Well, the biggest producer these days is Russia, by quite a long way. Next biggest is Botswana, and then Canada and Australia are about third equal. Australia being dominantly Argyle, there's really only one large mine here, and then other parts of southern Africa. There are diamonds found all over the world, but not in quantity. The ancient historical diamonds, like the Koh-i-Noor, came mostly from India and some from the eastern part of South America, particularly Brazil, but they're not large producers today. So it's Russia, Southern Africa, Canada, and Australia. The first place in which diamond was mined industrially is a town we now call Kimberley in South Africa. The first diamond was found in that area in 1867. It was a nice, about a 15-carat pebble that a child was playing with and somebody found, and it went up the line and was discovered to be a diamond, and that created a traditional rush like the gold rushes. It was a diamond rush. Thousands of diggers came and made their claims. This is the result. It's a famous picture, and it's of course complete anarchy and a total mess, because some of the claim operators were very diligent and dug very quickly, and some were less so, would spend all their time in the pub and dug more slowly. So these things went down at different rates, and of course started to collapse on each other. People were killed, and economically and financially very inefficient. So it was ripe for consolidation, and a man called Cecil John Rhodes came along and pretty much bought everybody up and created a company that was named eventually after the two Afrikaner farmers who owned the place. They were called De Beer. I think they bought the place for 50 quid and sold it for 6,300, something like that. But of course they didn't make the money they should have done. They just pushed off and bought another farm. And this was the Kimberley mine, and Kimberley was named after the colonial secretary of the day, Lord Kimberley, after whom the Western Australian Kimberley is named, by the way. So you don't have to go doing complicated exploration for diamond. You just go where there's a place called Kimberley, and you'll certainly find it. That's the Kimberley mine today. It's called the Big Hole. There is a theory that it's the largest hand-dug hole in the world. I think there's some competition for that. Anyone been to Kimberley? Yeah, if you get a chance, go, because it's really interesting. This is the Kimberley Mine Museum, which is a very good museum, and there's a platform you can go and look down the Big Hole. Notice another one there. There's about 4 or 5 of these kimberlite mines in the Kimberley area. They've all been worked for diamonds, and they're all worked out now. There's no more mining of new deposits in Kimberley going on anymore. But look at the shape. They're round. pipe-like structures. If you look at the more modern mines in Diavik in Canada owned by Rio Tinto, by the way, this is frozen for most of the year. They took this photograph in the summer. Again, it's a round structure. And these kimberlite emplacements are called kimberlite pipes. Diamonds are formed in the mantle, which is somewhere between 150 and 250 kilometers down, where there's carbon present and there's enough heat and enough pressure, which is favorable to the formation of diamonds. Diamonds are very old. They use isotope ratios to work out the age. The youngest ones are 500 million years old and the oldest about 3 billion. So nothing new has been done on the diamond front for a very long time. Kimberlite is not where the diamond formed, it's purely a transport medium. It's an explosive volcanic intrusion that brings the diamonds up from the mantle, creates a surface expression. Weathering then occurs, the diamonds are liberated and they will flow down drainage channels and along rivers and onto beaches and even into the sea. So De Beers has been mining diamonds off the west coast of southern Africa for 50 years using specially designed vessels to do that. It's quite important for the business. That's the Argyle plant. The mine actually up here on the hill. This is a classic diamond concentrator. I'll show you a flow sheet a little bit later. Argyle, interestingly, was I think the first, or certainly one of the first fly-in, fly-out operations. And CRA, now Rio, was a bit concerned about how they would manage this. And so they decided to make the village that they built for the fly-in, fly-out people very comfortable. It came to be called Club Argyle. For very good reason. It was a very nice setup, and that's a photograph of the recreation area. Nowadays, of course, you go to one of these sites and you live in a shipping container. Things are a little bit different, but in those days it was a real issue, and they also they had people studying the psychological effects of people flying in and flying out. It was quite interesting. Here's a graph of the production of natural diamond across the world from 2005 to last year. Last year, 134 million carats. It's about 27 tons in a unit that we can understand. The other interesting thing about this is the drop after the global financial crisis. Diamond is a discretionary purchase. It's a luxury. You don't need diamonds to live. So people don't buy them when they don't have any money. And therefore the market is a very difficult market to manage for that reason. And you can see the big drop after the global financial crisis. And it's never really got back to where it was. Now, I've been talking about natural diamond. That's diamonds made in nature. In the 1950s, a team at General Electric in the US made the first synthetic diamonds. And they did this essentially by to some extent, reproducing the conditions in the mantle. Very high pressure, very high temperature, carbon start, and you also have to do some quite clever chemistry to get it right. Shortly after that, De Beers made its first synthetic diamonds, and then a couple of other factories. And now it's a completely routine, large-scale industrial process. Synthetic diamond is a commodity, and everybody is dog makes the stuff. But you can see what you have to achieve. This is a very simplified phase diagram showing where diamond is stable with graphite. Pressure up here, temperature along here. 50,000 atmospheres is 333 metric tons per square inch, if you don't mind me confusing my unit. So 333 tons over an area like that, and 1500 degrees is 1500 degrees. So it's very extreme conditions, and you need some pretty special gear to do that, and these are some of the diamond presses that are used routinely today to manufacture diamond. Lots of different types of machine, but they all have the same thing in common. They squeeze a lot and they heat things up. You remember last year I said we mined about 27 tons of diamond. Getting reliable figures for synthetic diamond production is very difficult. It's a very commercial business and nobody ever tells you what they make. The best estimate back in 2010 was 8 billion carats. That's 1,600 tons compared to 27 tons. So a lot more synthetic is made than industrial. Most of it from China. China dominates the manufacture of synthetic diamond. And of course, most synthetic diamond goes into industrial applications. They've always been able to grow gem-sized diamonds synthetically, but it was never economic until about 10 years ago. About 10 years ago, the technology converged, and now you can go out and buy a synthetic diamond for your beloved. But they're a bit cheaper than the natural, so why would you do that? but plenty of people do. But dominantly it's used for industrial purposes, synthetic diamond. Just a small point. Synthetic diamond is diamond. It's just man-made. It's not a simulant. Cubic zirconia is a simulant. It's a completely different material made to pretend it's diamond. Synthetic diamond is real diamond. It has all the problems. And those properties are pretty extraordinary. I don't know whether diamond is in the Guinness Book of Records. It should be. It's the hardest substance known. Whatever you read on that, paragon of truth and virtue of the internet, whatever you read in the literature, it's the hardest substance known, bar none, man-made or natural. There are a couple of theoretical materials that have never actually been made that could be hard, but if you want hard stuff, this is the only game in town. Secondly, it has the highest thermal conductivity of any material. It's about 4 times that of copper at room temperature, so it conducts heat like a metal. And if I was fortunate enough to hold in my career a few very large diamonds, they feel cold like a metal. They heat up very quickly. Despite it being a good conductor of heat, it's also one of the world's best electrical insulators. So this is a combination of properties that is completely unique. There are some very rare diamonds that are found at, yes, you've guessed it, the Premier Mine, called Type 2Bs, which are in fact semiconductors that can be used in that role in electronic circuits. But the vast majority of diamonds are better electrical insulators than most commercial insulators. In terms of its gem properties, it doesn't have the highest refractive index of any material, but it certainly does when it comes to gemstones. Refractive index tells how much light bends when it goes from one medium like air into another like a diamond. And that particular property, if the diamond cutter is skilled, they can achieve essentially total internal reflection of all the light that comes into the diamond, so it all comes out to pretty much the same place, and that's why it's bright and shiny and sparkling. Dispersion means the property of refracting lights of different wavelengths differently. And it has a very high, relatively high dispersion, and that gives it its fire and the colour that you see in the diamond. So those two combinations are why people like diamonds as jewelry. It's also the least compressible substance known. So if you squeeze it, it doesn't deform. That means it has a high coefficient of restitution, and that means if you drop it on a hard surface, they bounce. Diamonds bounce. And I found this to my cost. At a very early stage of my fledgling career, I was given charge of this, that's my hand on the right, of this pile of diamonds, a very beautiful set of 250 green octahedral stones. They were sorted from a particular source. And I was tasked with using them as tracers to run through a comminution circuit to see if the diamonds broke. I was actually walking up some stairs in the consulate and I tripped, and it was in a little beaker, and I went like that, and went everywhere, and bounced everywhere. I thought, that's it. I wanted to be a fireman, I'm going to be a fireman. I'm not going to be a metallurgist anymore. Anyway, a colleague of mine and I spent the rest of the day tracking these diamonds down. We got them all back. I didn't tell anybody at the time, so I got away with it. But the point was, you would be astonished at where those diamonds got to because they bounce. I had a death wish because a few weeks after that I drove the general manager's Mercedes into the back of an oil tanker. Further attempt to limit my career prospects. They were very angry with me that I hadn't written it off because then you could have got a new one. Anyway, I got away with that one as well. And some of the properties lead to great beauty. This is one of my favourite photographs. It's a large 75 carat diamond, flat, about the shape and size of a matchbox. It's a 2B, it's very rare, and irradiated under X-rays, it glows this fantastic blue colour, just unbelievably beautiful. So these very special properties lead to a wide range of industrial applications. It has been said, with some merit I think, that our material civilization that we enjoy is only possible because of diamond, because it does all the heavy lifting. And of course dominantly it's an abrasive, so cutting, grinding, polishing, drilling. But it has a lot of other esoteric uses as well that come from some of those other properties we talked about. It's a heat sink because it conducts heat so well, and is also an electrical insulator. It can be a window for both high-powered lasers and for instruments that need to take in infrared or microwave radiation. These are unusual combinations of abilities. Some are semiconductors. It can be used as surgical knives, which are A sharp and B last forever. And physicists, when they do very, very high pressure experiments in high pressure apparatus, they'll use diamonds as the anvils in that apparatus. Some of you may have an angle grinder at home. This is a picture of an angle grinder blade with diamonds in the surface. And here are some other pictures. Here's a whole bunch of tools of various kinds for cutting and sawing and so on. Mick Kilmartin in the workshop, I said to him, "Have you got any diamond tools?" He said, "Yes, I've got one. Here it is. I'll pass it around for you to have a quick look at it." It's not very exciting or beautiful, but it's really important. He uses it for dressing wheels in the workshop, and the diamond's right on the end there. So, and he would really like it back too. So here's a drill bit that you'd be familiar with for geological exploration and other purposes. Next time you're in an aeroplane, and if you're sitting in the window seat and you're about to take off, look down at the runway. If it's a large capital city airport, you'll see thousands of slots cut in the runway. That's to drain water so that aircraft don't aquaplane. Those slots are all cut by diamond saws. It's the only way you can really do it. Maybe you can see it doing just that. But this is my favourite industrial application. This is a diamond window that, as we speak, is standing on the surface of the planet Venus. It was sent there by NASA, the Pioneer 13 probe in 1978. Here it is in its replacement, and here it is while it was being set up. It's a 13-carat perfect window from, yes, you guessed it, the Premier Mine. Why a diamond? Well, Venus is not a very nice place. The surface temperature, I think, is 460 degrees. It's about 90 atmospheres. It rains sulfuric acid. It's not a good place. They wanted to analyze the composition of the atmosphere, so they needed light from the atmosphere, but they needed, obviously, to screen the instrument from these nasty conditions. And the window that they used to do that had to be able to pass infrared radiation. There's only one material that gets a tick in all those boxes, and that's diamond. Being NASA, they built two. They have a redundancy policy. I don't know where the second one ended up. It's not in Venus, it's somewhere else. Well, when we buy a diamond or get interested in diamonds, really the price is what we worry about, and what determines the price? Well, it's the famous 4 C's, I'm sure many of you are familiar with. Carats, the weight; clarity, which is the presence or otherwise of flaws or inclusions; colour; and how it's been cut. On clarity, there's a definition that a diamond is flawless if there are no scratches, inclusions, or flaws visible under 10 times magnification. So next time you buy a diamond, all you need is one of these little things. It's called a loop. It's 10 times. Go to the jeweler and take this out and take the diamond. Now, A, you'll appear to be really expert in this, but let me tell you, it's much easier than you think to find flaws in a diamond. It's better for it not to be set. If you can have it for free, it's much easier. And I have done that on a few occasions. And I have actually said to one of the jeweler, a bit like that, it's like a flaw, it's good. So I'm not an expert. It's very easy to do. So just buy yourself it 10 times and take it to next time you buy a diamond, which I'm sure after today will be tomorrow. Let's look at carats. The problem with diamonds. So if you're a gold miner, you know what the price of gold is. Look at that. If you're a copper miner, you know what the price of copper is. Diamonds are different. Every diamond is different, and every diamond will command a different price because of this combination of C's, other than the cut, which of course only comes later. And the trouble with the effect of weight is that it's extremely non-linear. You might think a 2-carat diamond would be twice as valuable as a 1-carat, but it doesn't work like that. It's 5 to 10 times valuable. So the price per carat goes up rapidly. So if you want it in the form of a graph, which we love, don't we? Here's the constant price per carat, and here's what really happens. So a 2-carat diamond you might think is twice as valuable as a 1-carat, but it's not. It's maybe 10 times as valuable. And that has to be, of course, part of the determination of the value of a new diamond project. What is the diamond size distribution as well as quality and so on. And for this really nasty effect, that unfortunately leaves us as normal people operating somewhere down here because we just can't afford the dollars. It's only the big players who operate up here. So, this is the JK. I've got to tell you something about the mineral processing of diamond. And again, it's very peculiar material, and therefore the constraints on how you design a diamond concentrator are quite different to those of other commodities. The first problem is diamonds are very rare. For a start, most kimberlites don't have diamond at all, but the ones that do, the diamond is there in very, very small quantities. So the richest diamond mine in the world was Argyle when it started, which was 6 carats per ton. Now, when I was working with the Beers, the unit you used was carats per 100 tons. Right? Argyle went straight to multiply that by 100 and went to 6 carats per ton, which works out as 1.2 parts per million. The lowest grade mine in the world, there are several mines that compete for that rather unfortunate prize, but let's take that saying in the mountain kingdom of Lesotho in southern Africa, 0.006 parts per million. So there's a 200 multiple between those two numbers. Remember, 1% is 10,000 parts per million. So 0.5% copper ore is 5,000 parts per million. So conventional base metals that we're all used to have a grade in mass per unit mass of ore tens to hundreds of thousands of times larger than diamond. So that's problem number one. Secondly, the other constraints really come from its physical nature. So, for example, diamond operations are not interested in anything below about 2 millimeters. It used to be 0.5 millimeter, but you can't get above that stuff anymore. So 2 millimeters, mostly people just screen it out and throw it away. And of course, that's the exact opposite for most of the commodities that we're using. Secondly, you're talking about physically discrete particles whose properties completely define their value, which is not true of, say, a base metal or a gold operation. And that also means that you've got to preserve that integrity and not break it. Diamonds are the hardest substance known, but they're brittle, as the guy underground at Premier found out when he hit it with a hammer. So crushing diamonds and reducing their value is a major problem, so you have to worry about how you do that. They're chemically inert, so you can't use leaching. And I've made this point, the price is not constant. So that gives us some constraints when you're worrying about how to recover diamond from the mined ore. Firstly, the treatment costs have got to be really low because the value of the ore is not particularly high. Recovery efficiency must be very high. Karowe Mine that I mentioned to you has recovered the second largest diamond ever 3 years ago. A couple of years ago it recovered 4 diamonds totaling from memory 2,600 carats. They were sold for $154 million US, which was more than the cost of bringing the mine into production. 4 diamonds. So you've got to get them all. You can't lose one or break it because you are tens of millions of dollars in the red as a result. So recovery efficiency must be high. The nature of the diamond means you've got to use mainly physical processing methods, and because of the need to avoid crushing diamond, you've got to liberate carefully, and that's done in stages. So here are some of the properties of diamond that are used in its recovery, and some of them are really quite ordinary. Density is the dominant one. So the rock-forming minerals in kimberlite, densities of the usual 2.6, 2.7. Diamond is 3.52, so it's very easy to run a dense medium plant at about 3 and throw 99% of the stuff away. The trouble is the 1% you've got left, the diamond is still the rarest component, and there's lots of stuff denser than diamond. So it's not a selective process, but it's very good at getting the bulk down. X-ray transmission is a very new technique that's being used. I'll show you the machine in a moment, but this is X-ray transmission sorting. Diamond has a very low X-ray cross-section. It's transparent to X-ray. So if you put a pile of rocks down in a diamond in the middle of it, an X-ray, the diamond will look like a hole. So they've now developed a sorter to exploit that. But the classical old X-ray sorting technique is X-ray luminescence. Diamonds give off light when they are irradiated by X-rays. So does cement, by the way, so that makes a bit of a problem. But, so X-ray sorting by luminescence has been around for 50 years. We don't recover diamonds by flotation, but if they were 2 orders of magnitude finer, we could, because they are naturally hydrophobic. Most of them, not all of them, most of them. But the diamond people have used an analogy to flotation, which is grease separation. So we actually call it oleophilicity rather than hydrophobicity. So it likes oil, it likes grease. And that's a very selective technique. Very old-fashioned, but it's still used today. You can go out and buy a diamond grease total if you want to. You can get concentration ratios of 2,000 or 3,000 to 1, no problem. Magnetism, a lot of the heavy minerals that diamond comes with are magnetic, so you can remove them by magnetic separation. Diamond, of course, is non-magnetic. They're shiny, so in the old days we had reflectance optical sources for separating the diamond from other material. Not so much these days. And of course they're insulators, so high tension separation is a possibility and was used many years ago, not today. The Raman signature of diamond is very specific. So you've got a Raman laser sorter, which has been developed now for final stage sorting. It's very specific to diamond, and that's a modern development. And of course, it's chemically inert. So those are the properties that are used in practice. And let me just walk you through, because this is the JK Centre, I'm going to show you a flow sheet. Let me walk you through a generalised, standard, classical diamond recovery flow sheet. Let's start with 100 tons with 100 carats in it, 20 grams. Initial comminution at a coarse stage, and then very quickly you want to set the lower operating size of, let's say, 2 millimeters. So you chuck out all the slimes and fines and the weathered material. Some kimberlites are heavily weathered, so there's lots of clays, we're not going to do that. But let's say that gets rid of 20 tons. Then you would go into the first stage of concentration and density would be almost certainly what you would use in almost all cases. So dense medium cyclones would be the standard way. And they are very effective. You would take less than a 1% concentrate from that step. So our 80 tons might be down to half a ton. But half a ton, that's 500 kilograms, has got 20 grams in it. It's still not there in very high quality. So we've got to do some more concentration, perhaps another density step, magnetic separation to get rid of some of the high density stuff. And then we go into what diamond people rather misleadingly call recovery, which is the final stages. And there's a whole range of tricks to use there. Mostly X-ray luminescent sorting, grease separation possibly, more mag set, and in the old days, high tension and colour. And out of that 500 kilograms, you might have 1 kilogram, and then final sorting, almost always hand sorting, by the way. You can do chemical dissolution. If you've got hydrofluoric acid or high temperature caustic fusion, you can dissolve everything except diamond. Both of those are very nasty materials indeed. We used to have the largest supply of hydrofluoric acid in the world at one point. We were dissolving 1 ton quantities of geological samples. It's a really bad idea, let me tell you. You wouldn't be allowed to do it today, I don't think. But really, this is hand sorting, and if you're lucky and you've done a good job, you'll get most of your 20 grams from your here are pictures of diamond in situ. So this is a diamond, you can just see it there, in a piece of conglomerate, which is just a cemented sandstone, so that's a semi-alluvial. This is the origin, piece of diamond in a piece of kimberlite. Diamond in kimberlite, we used to call it, or dip for short. And metallurgists don't have a very sophisticated sense of humour, so I'll leave you to work out how that was used. Now these used to be incredibly rare specimens. You only saw them in museums. We put an X-ray sorter, a luminescence sorter at the front end of the Premier plant years ago, and it found lots and lots of these things. And this was wonderful for us at the lab, because for the first time ever we could study at a decent rate the interface between diamond and kimberlite. How is it locked in the kimberlite? And that allowed us to take pictures like this. So here's the diamond, here's the body of the kimberlite rock, and kimberlite is basically a basic rock dominantly olivine. So this is olivine, but this is altered olivine, this is serpentine. And serpentine is quite soft. And the old timers, would be poo-poo, we were the scientists who were PhDs. The old timers, but they used to say, diamond is easy, it just pops out of the rock when you squeeze it and crush it. Pops out. What a lot of rubbish. They were dead right. And they were dead right for two reasons. One is this soft interface, and the other only became apparent when some work was done here at the JK by Nina Jubilee, and Sharma will remember that work, and some others here. We were doing some work for De Beers, and he used finite element modeling to show that if you inserted a very stiff component, stiffness is the key, i.e. a diamond, into a piece of rock and then loaded it as you do in crushing, the lines of stress would be attracted essentially towards that stiff component. And when the rock then fractured, it fractured around the stiff component. So the old timers were actually dead right. And that's why you get those sorts of additions. And Sharma and I were talking this morning. This is the photograph you might remember, Sharma. This was work done by our blasting group many years ago, also on kimberlite, and they used a detonator to blast a bit of kimberlite and burn it down. There's a diamond selectively liberated with the crack going right through the middle of it. And if you remember these diamond and kimberlite, same thing. The rock has broken around the diamond. So for us, the diamond business, it's actually easier than it is in other businesses to liberate. But the technologies used are completely conventional. So here are cone crushers at Premier. The only people who use ag mills in diamond are the Russians. They use them all the time. There's only one ag mill in a western diamond mine, and I'll talk about that just briefly in a moment. Scrubbers for cleaning the stuff up. If you've got a lot of clay, you need to wash. High pressure grinding rolls. The high pressure grinding rolls was first introduced into mineral processing by us at De Beers in the early 1980s because there was evidence of improved liberation. Up to then it had never been used in cement. So the first use of high pressure grinding rolls in minerals was in fact in diamonds. And then density separation with dense medium cyclones. These are the gravity fed cyclones at the Argyle diamond mines. And here's the new machine. This is an X-ray transmission sorter, which is starting to be thought about at the front end of the process, where you get the big diamonds to get them before you crush them. And here's some grease separation. This is the old-fashioned grease table. It's a batch process that slowly flows over grease-lined steps. Diamonds stick to the grease, the other stuff flows over, and after a while you stop it and you scrape it off, you melt the grease, recover the solids, and then do it again. As you can see, it's not a very high security environment. So they invented a continuous belt, grease belt, but essentially it does the same thing. I went on the internet a few weeks ago and I was comparing this to, you can still buy one of these things new, and they're still making them because they work really well. And X-ray luminescence sorting then dominates the final stages of diamond recovery. This is a picture took many years ago, but it's a really great picture because it shows you the fundamentals of automatic sorting. Here's a belt, particles, in this case are gravity concentrated in free fall. Here's an X-ray tube, the beam comes down here, the diamonds light up, this is in a light-tight box. Here are the photomultiplier tubes that detect the light, and here are the air ejectors that spit it out of the stream. So this is a classic sorting principle. And that's a modern version. If you go to a couple of companies around the world, you can buy a modern version of that. These are actually dual wavelengths, so they're a little bit more selective than the other single wavelengths. And finally, hand sorting in some form or Let me just finish off by telling you a little bit about this Karowe Mine, because it's breaking all the rules. It's a very remarkable place. They have more than their fair share of large diamonds. That dominates their thinking in terms of recovery. So here's South Africa, here's Botswana. Gaborone is the capital. Jubilee is one of the De Beers operations, and De Beers in the 1960s found a great kimberlite province up here, of many kimberlite finds, some of them with diamonds, including Arapa and Letlhakane, which are De Beers operations. I worked on Arapa in 1971. Karowe they also found, but rejected as being too low grade. You don't always get these things right. And an upstart outfit that knew nothing about diamonds came along and said, oh no, this stuff's actually a bit higher grade than we thought, and it's got real whoppers in it. So they've made a good business out of it. And there are some of the products of Karowe, and they, as I say, this is the place that had 4 diamonds worth 154 million that paid for the mine. All these diamonds are over 200 carats. This is knocking on the door of 500. So they do get big diamonds and they sell for a lot of money. So let's look at another flow sheet. This is the last one. And it's because it's a bit different to all the others. The yellow bits are novel for Western style diamond concentrators. But there are some others that are the same. So primary crushing, an ag mill. And I understand, I actually wrote a paper about this and I read it, that it wasn't there for any subtle diamond reasons. It was cheaper and had a smaller footprint than the crushing alternatives. So they put it in for that reason. But the Russians use them all the time, and so the argument was they should be okay. I wouldn't use that argument because the Russians use it. It's not a good argument, by the way. We won't go there today. Conventional pebble crusher, and then some sizing, get rid of the slimes and grits as soon as possible. Take the other stuff and screen it again, and the oversize goes into the X-ray transmission sorters. I just showed you the big one. So these are high tonnage machines looking for very coarse diamonds. The coarse tails get recrushed, so this stage crushing idea is very important. Concentrate goes into final sorting, and the undersize from here, for this stage, goes into conventional dense medium. So that might be about 12 mil. I'm not sure if it's exactly 12, but it would be something like that. So plus 12 all goes into X-ray sorting to get the big ones, and minus 12 goes to conventional dense medium. And then conventional X-ray luminescence, and then fine sorting. So these two are novel, and I really admire them. They broke some rules. They did things that the old timers said shouldn't be done, and they got it right. They're making an absolute squeak. Well, are there diamonds in space? Just thought you'd like to. I'm sure that's at the front of your mind. The question you were going to answer that question for is absolutely yes. There's no doubt about it. How do we know? Well, lots of reasons. Number one, about 3% of the carbon in meteorites is present in nanodiamond. Other diamond meteorites have been found with coarser diamond. The physicists and astrophysicists and astronomers say that the universe is probably full of diamond because stars make carbon, and the conditions for diamond to form are present in many parts of the observable universe. They think that there are diamonds in large quantities present at the center of the 2 solar system gas giants, Uranus and Neptune, because there's lots of carbon in the atmosphere, methane and so on, ammonia, and the conditions at the center of those planets are suitable for diamond. One extrasolar planet has been found with a strong carbon signature, and looking at it, one of the controversial theories is that the entire planet is made of diamond. The diamond market in the UK, in this part of the world, could do without, I think, a planet made entirely of diamond. The market would be somewhat damaged. But so yes, there's diamond in the universe without any damage. And one last point, and this is for the ladies. It's a melancholy fact that old married couples face the likelihood that the woman will outlive the man. And so widows are commoner than widowers. There's 2 reasons for it. One is men do not live as long as women because, of course, they work themselves to death. And the other reason is that they do die young, so there's no doubt about that. And the other reason, of course, is that generally the man is older than the woman. So widows are commoner than widowers. But there's a small recompense now available to widows. I came across this headline in a newspaper Australian Daily Mail. I turned my dead husband into a diamond. The bizarre trend for making keepsakes from one's ashes. Now, this is not a joke. You can do it. You can get on the internet, you can find companies, needless to say almost all in America, who will take the ashes of a loved one or a pet and, you know, just make a synthetic diamond out of it. No problem at all.
Big dude, that's what
So, associated with the story was this grieving widow trying desperately to look sad, and then her husband.
There's a lot of nitrogen going on there.
Yeah, that's right. Well, it's yellow because of the nitrogen in the acid. But I'm told you can have any colour you like because they can leach the colour out and do it. So, ladies, the old guy may not have been much use to you when he was alive, but he could be really valuable to you. Thanks very much for listening.